Hello, pre-calculus students. Today we're going to learn how to use exponential and logarithmic functions in practical problems. Well, they're not really practical because most of us don't deal with radioactive isotopes and things of that nature, but you can see at least some real-world examples of how exponential and logarithm functions are used. So, here are some examples up on the screen. First one we'll look at is compound interest. We know that if you get interest a specific number of times a year, that's discrete. You get interest here and here and here, maybe once a day or once every month or once a quarter. You'd use this formula. Now, I don't know that anybody uses continuous interest outside of a math class. I think this, like simple interest, is just one of those things that we do to, oh, it's kind of cool. But here's the formula that would work for that. So if P is the principal, which is the amount of money that you save, and let's just say that's $1,000, and we're going to let the interest rate be 1% a year. And right now, interest rates for on a savings account are about 1/100th of this, or 1/100th of a percent per year, which means for every $100 you get about a penny. That's 1/100th of 1%. So maybe this is a certificate of deposit. So assuming that interest is compounded daily, how long will it take for your money to double? You might say, well, I'm getting 1% a year, so it should take about 100 years to add 100% to it. But keep in mind that you're going to be getting interest on your interest each day. So it should take less than 100 years. Let's figure it out. So here's the formula. We want our money to double, it needs to get to $2,000. 1% is 0.01, and we get interest daily. So how many years? Well, it's going to be 365 days a year times the number of years. Solve for T. We'll divide both sides by 1,000. And then take the natural log of both sides. And again, you could have chosen the common log, but to me, writing ln is easier than writing log. That's the only reason I chose natural log. So take the log of both sides, the natural log, and you'll get the natural log of this. You can bring the exponent out front. Now divide both sides by everything necessary to leave t all alone over here. Notice that I have not touched a calculator. Some of you are going to want to write, and you're going to want to approximate this, and then you're going to want to approximate this. You're going to build so many approximations into your calculations that you're going to be off in the end. Don't need to do that. Solve for your variable first, like I did. I have an exact answer here for my variable t. Now I can substitute this, or I can use a calculator on this all at once. The calculator will drag everything out to 9 decimal places or however much. There'll be no rounding at all, beyond what the calculator does. And I can round the final answer, and that'll be much more precise than doing these interim calculations and rounding them. So you should pause the computer right now, pause the video, type this into your calculator, see what answer you get, and see if your answer matches mine. If it does, then you know that you're doing it correctly. And here's my answer. Okay, so that's exponential growth. Exponential decay. Radioactive substances. You may have learned in physics that substances that are radioactive, like uranium, they're constantly throwing off electrons, and they actually change into other metals. So some materials have a half-life measured in seconds, some have a half-life measured in thousands of years. So what happens is, let's just say a half-life is 1,000 years. So if you have you know, 1 kilogram of whatever it is that has a half-life of 1,000 years. 1,000 years from now, half of it will be something else. It doesn't disappear. It can, you know, by losing all those electrons, it converts into something else. So you'd still have half a kilogram of whatever you started with and another half a kilogram of some other metal. After another 1,000 years, so after 2,000 years, you're down to 1/4 of the original material and 3/4 something else. And eventually, you know, as you keep going down to infinity, these things, I think they all turn into lead eventually. Maybe I'm wrong on that, but I think they all eventually turn into lead. So here's our formula. So here's what the mass of remaining after T, mass of the original material remaining after T years is, here's the original mass, and this is how much it cuts down. There's a constant for every radioactive substance. You know, uranium has a different constant K than carbon-14 does, which has a different constant than cesium does. So we have to find those constants, and then we can look at how much of a material remains or how long it will take until 99% of your radioactive substance is gone. So I did one of the problems in our book. And again, the first part says, we know that carbon-14 has a half-life of this many years. What does that mean? That means after this many years, half of the carbon-14 is gone. It's converted into some other metal and or some other material. So after 5,715 years, only half of the carbon-14 is still carbon-14. After another 5,715 years, well, you got half of that half, so only 1/4 of the original amount is still carbon-14. The rest is something else. So how can we solve for that constant K for carbon-14? Well, and then if we start with 6.5 grams of carbon-14, how much is left after 1,000 years? Well, we know that half of it's left after 5,715 years. So we know that there's got to be a lot more than half after only 1,000 years. So first thing we have to do is solve for K. Good thing we know the half-life. So half of 6.5 is 3 1/4. And I know that I would get 3 1/4 grams after 5,715 years. So I divide both sides by 6.5, so there's my 1/2. So this quantity over here has got to equal 1/2. Take the natural log of both sides, and this time I chose natural log because I have an E, not just because it was more convenient. Take the natural log of both sides, and divide by this negative 5,715 to get K, and you see it's a very small number. I went to 6 significant figures. The 3 zeros don't count as significant figures. Now, if you say even that's too much rounding, you could have just left this like so, multiplied it by 1,000, raised E to that power and multiplied by 6.5, and maybe you'd get a little bit off, but I think 6 significant figures is probably sufficient. So if we said it would be more than 1/2 of the amount remaining because it was only 1,000 instead of 5,700 years. And we went, after 1,000 years, we went from 6.5 grams of carbon-14 down to only 5.76. So still well over half like we anticipated. Where have you heard of carbon-14 before? Well, maybe you've heard of radiocarbon dating, or also called carbon-14 dating. And how archaeologists can use that to tell how old something is. Maybe you want to read page 241 of your textbook on that, because it's pretty interesting. So we've done an example of radioactive growth, which is radioactive, of exponential growth. which was our compound interest. We just did radioactive decay, which is our exponential decay example. Now let's do a log example. And in California, where we currently are, earthquakes are kind of a big deal. And we measure the magnitude of earthquakes on the Richter scale. And this is your magnitude on the Richter scale. We have some quantity of energy that's released, some minimal quantity. We say, man, if you don't release that much energy, it's not really an earthquake. It's just dropping a rock on the earth. It's not the earth isn't quaking. So we measure the energy of the earthquake wave, and we divide it by this, minimal amount. So we know how many times stronger than this minimum earthquake is the earthquake we're measuring. Now, because that varies so much, it can go from a little bit to this huge number. Well, we don't want to be dealing with huge numbers, so we just take the logarithm of it, base 10. In fact, I'll just leave it log. So what we do is we measure, we figure out I over I sub 0, which is how many times the energy of this, minimal earthquake is the earthquake you're measuring have. Then you take the log of that, and that's your number on the Richter scale. So how many times the energy of a magnitude 5 earthquake does a magnitude 7 earthquake have? So I'm going to say I5 is that intensity, I7 is this intensity, and I want to find I7 divided by I5. Now, you know what, the only thing I will say on this, now that I think about it, every time I've ever seen this written, it's written this way, which assumes log base 10. But some math people, and I don't know if the physicists who work on this, they use log to represent natural log. They don't ever consider common log. So I don't know if this is, to be honest, there's a possibility that that's common log. I don't know. I'm going to assume log base 10 because that's how they've written it until I find out differently. So anyway, I know that the log magnitude 7 earthquake is the log of my intensity, however many whatever energy is, they measure energy of earthquake waves in, divided by I has got to be 7. Take the log of it. Same with the magnitude 5. So I'm going to take 10 to both powers. Maybe I should have taken E. As I said, maybe that is a natural log. But for right now, we'll just assume common log. So I'm going to raise 10 to both sides here and 10 to both sides here. The 10 to the exponential base 10 and the log base 10 will undo each other. And I'm left with a magnitude 7 earthquake has 10 million times the energy release of the most minimal earthquake. And a magnitude 5 earthquake has 10 to the 5th, what's that, 100,000 times the energy of the minimal earthquake. So if I want to do I to the 7 divided by I to the 5, well, I can do this divided by this. You can see that the i's cancel, and I do get I to the 7 over I to the 5th. So this divided by this, 10 to the 7th divided by 10 to the 5th, 200. So if I've done the correct logarithm, a magnitude 7 earthquake has 200 times the energy of a magnitude 5 earthquake. So those are our 3 examples. Hope you found something interesting in at least one of them. Have a great day.